Sitting here fine, right? Yeah, this timer disappeared, so I can just press it. Problems that if there's more questions than okay.
Exceed my time back. Okay, maybe I should put one of these.
And John, Michelle was going to say something.
Oh, okay. Yeah. Do you think she'll use the regular mic?
Yeah.
Okay. Let me get this out of here just because this will cause problems. Potentially. Yeah. Just check. Here? I don't know. All right. Great. Thanks. And it is on.
And you have that.
Yeah,
I
thanks.
will wave at you when you have 5 minutes left.
Okay.
Sometimes when you get into it, you just don't look. So.
Yeah, I know. Thanks. Yeah, no, feel free to do anything. Some jumping jacks are all included.
You hit 0 and you're still talking. I'll come stand next.
Yeah.
You don't need anything on. I can just pull up his slides now.
Yeah, Michelle was just going to welcome everybody.
Oh, okay.
Yeah.
It's just so difficult to fit in here. All right, cool. I think if you hit that green button, at least for a PDF,
It's always
it's
different.
the easy way. Yeah, I know.
Fairness.
Yeah, well, I just saw somebody else do it.
Yeah.
And then I've got a clicker. Let me.
I just want to make sure that someone else's PDF,
Oh.
the top page of the bottom of the previous page was showing up. So can you just go to the
Here?
next slide? Yeah.
Yep.
Okay, good.
Okay. Get this out of here. Get something to drink. Is there some feedback?
Yeah.
All right, good morning, folks. Thanks very much for being here bright and early and caffeinated. And yesterday, I don't know about you all, but yesterday I think was one of the most fun days I have ever had at a conference ever. So thank you to everybody for, participation and excitement and just making this environment one where we're all learning and sharing ideas and debating and growing. I have been having an excellent time. I am delighted to introduce this morning's first speaker, John Wu, who will be talking about automated mission classification with large language models. So let's please welcome John.
Thank you. Thanks, Michelle. I just want to check, everybody good with the mic? I can be pretty loud, thank you. Okay. Yeah, so it's my pleasure to chat with you bright and early about automated telescope bibliographies, mission classification, by using language AI. And so before I get started, I should say I'm the applied AI scientist here in the data science mission office, which is headed by Michelle, actually. And we've got a lot of different activities going on with AI here. And sometimes when we talk so much about machines, it's important to remember why we're doing what we do, why we do astrophysics, why we work and collaborate with each other. And I was talking to Joe Chuka yesterday, who really reminded the centrality of focusing on people, right? Like, this is what brings joy, is that actually, like, a lot of us do astronomy because the people are just amazing. And I'm privileged to be able to work with many of the people whose names are listed here. There are many others who are not, but deserve much credit. And a lot of the work that I'm doing is founded on the amazing things that they've done, not just on the technical side, but also on the policy side, the strategy side. And so I want to take a moment to acknowledge that these are all vital parts of why we do what we do, why we do astronomy, and why we try to enable new science. And it's exactly that last bit, enabling new science, and in fact, understand the progress of science, that automated mission classification becomes so important. We have seen that the number of publications per year, which is shown on the y-axis here, is rising rapidly and consistently. This is from ADS, so I just did a quick query over the astronomy collection, and you're seeing things like non-refereed papers, not just journal articles, but also, or not just archive papers, but also abstracts and things like that in the blue line there, and that's steeply rising, and so is the number of refereed papers. And that rate of progress is outpacing our capacity to manually read or review or even label those papers. However, this literature is really a treasure trove for us. It helps us know what the scientific impacts of our telescopes are. And so if we're going to go and spend billions of dollars to launch observatories into space, we should know what it's actually doing for the community. And one good way to track that is actually to measure the number of publications. And one thing that you might not appreciate is that the number of publications, and in this case, the fraction of publications that have archival data, which are not initially requested by the observers, by the authors of the paper, is something like 50% of papers. And so our literature not only shows us how important NASA is and other funding organizations are to enabling astronomy, but they also tell us how valuable our archives are. Another paper that just recently came out by Dick Shaw et al., in behalf of the MAST team, is just looking at the value of the Mikulski archive for space telescopes, shows that already 30% of JWST science is archival. And so this is kind of an interesting plot. I'll just walk you through it real quick. This is the number of publications per year, specifically for HST, which is kind of in this lighter colored filled colors here, starting from 1990 or 1991 here, and going to basically the present day. And at the way right side, at the blip on the right side there, you see this explosion of new papers in the darker shades, and that's showing how JWST is enabling a lot of science. And if you're wondering what the heck is going on with the y-axis here, on the traditionally negative side, the lower side, is actually increasing, showing how many guest observer program papers there are. So science papers that were requested by somebody proposing to observe some target. What you see, of course, then, if you look at the sort of the positive y-axis here, is that actually there's, in many cases, more archival, or at least partially archival, science papers that actually arose from Hubble observations and already JWST, even though the JWST science operations only started in 2022. And so again, what this is telling us is that there is a huge amount of archival science out there, and it's extremely valuable to know how many papers and which papers are actually linked to JWST or HST or some other mission science. So how do we actually know this? This is the million-dollar question. In fact, it's a very scary question because somebody has to read all of them, right? And as we just said, there's a lot more coming. And with Nancy Grace Roman launching, this is going to start to get unscalable. Somebody has to read these papers, right? Somebody has to go and review these and identify the labels, ensure that we're doing this robustly, we're not doing this in any sense of bias. And so a lot of what Dick Shaw's paper, looking at the legacy of the MAST archive, thinks about, is focused on this. And a lot of what Jinmi will be talking about as well is about enabling this, right? Okay. So I feel like the core thesis here, that if you know this Simpsons quote, this is like one of my favorites. I actually put it in a paper last year. Because, okay, so I realize the font is kind of ridiculous, right? If you work with LLMs, you'll know that they are not just a solution, they're also a cause to the problem. And so in this way, there's kind of a love-hate relationship here. They are the cause of a lot of problems in the literature, and they're the solution to a lot of problems in literature. I'm going to talk mostly about the solutions for now, but you should be aware that LLMs are causing all sorts of other issues. All right, so with all that out of the way, let's go and jump into this roadmap. I want to talk next about the actual system design, how we design these LLMs for mission classification. And then later I'm going to talk a bit about evaluation, metrics, building a golden sample for evaluation, and then some results in two separate tasks here. All right. So the central aim here is saying, is basically this question: given a paper's text and possibly some other metadata, how can we label it as a science paper, maybe an engineering or instrumentation paper, just a passing mention, or maybe something totally unrelated, right? Like it shouldn't have been even related for some given mission, Hubble, JWST, Chandra, TESS, your favorite mission here, SphereX. And this is a pretty important question. This is one that I think a lot of the archives are grappling with. And so, so this is what we're aiming to solve here. And the way we tackle this is by using a 3-stage LLM system. So I'm going to show a flowchart in a minute, but I want to paint a picture with words first. We are using, in this case, closed source models. So only querying them using API calls, in this case, OpenAI. But this can be easily adapted to use open weights models. The first step is to do some simple keyword filtering. The idea is that if you know that you've got a mission, like let's say Hubble, there are certain keywords, like for example, all the names of the instruments on Hubble, with C3 or COS, COS, or STS, or so on. And the point here is to emphasize completeness. At this stage, we don't want to miss any potential mentions, but we end up with something that is highly complete, but lots and lots of false positives, right? You're triggering on every single possible keyword. That's the first step. Now, the second step is something like what are traditionally called re-rankers. Re-rankers are these types of language models that essentially know, given a query, how relevant is usually a short piece of text to that initial query. And so you would have a separate re-ranking prompt that looks something like, okay, you've seen all the text snippets that relate to Hubble, the Hubble Space Telescope. Is this something about, is this really something about the Hubble Space Telescope science papers, right? Like, is this really about doing science with the Hubble Space Telescope, or is it just a passing mention? Is somebody else, talking about the Hubble Space Telescope or some theoretical survey program that nobody has yet done? And that re-ranking allows you to resort all of these text snippets. And at this point is when you can start doing things like filtering out the sort of false positives, things that you don't really want. And you can also do structured extraction, turning a lot of these into basically schema-validated, type-checked quantities. So you might say that this must be, you have to give an integer here, you have to give a floating point number, et cetera. So that's what I mean by structured extraction. And then the final part is actually the LLM prediction, right? Doing a classification based on the top-ranked text snippets, so the most relevant snippets, and in the previous stage, actually, we also forced the LLM to give justifications. So it's basically doing an internal, manually enforced reasoning or rationale. And the nice thing about this is that there's no real training needed. Of course, evaluation is everything. We're going to talk more about that in a second. But what we do find is that this demonstrates strong performance via purely in-context learning. You're just giving it text, and you're saying, you're smart enough to figure this out, right? Like, you kind of know what a Hubble paper might look like. You might know what a Roman paper looks like, even though you've never seen it, because you kind of know what a science paper looks like. So there's no training needed, and that's actually kind of a big boon. And this kind of code is also easily adaptable for multiple use cases. And I'm going to talk about these more in a moment, too, for JWST preprint automation, which is helpful for identifying DOIs or compliance for some DOI tasks that we need. And then also for actually this Kaggle challenge with WASP. And so then, and as I said, we're using the OpenAI API, but we can easily adapt this for open weight LLMs. All right. I'm going to say the same thing I just said, but now in pictures. So what we begin with is the actual text corpus, right? And so you imagine that there's this ginormous JSON blob or something like this, which has, all of the bib codes, basically all the unique identifiers for each paper, and it's got things like the titles, the abstract, and the body text, and possibly a whole bunch of other things, right? The names of the authors, the year of publication, and so on. In our case, we work with the paper plain text, and sometimes we actually work directly with archive PDFs, so we actually need to convert a PDF into plain text, and then just grab some of the relevant stuff. One note, the body text, if you're scraping it out of a PDF, can have shredded components of figure captions and weird parts of tables, and unfortunately the references all kind of get tacked in there. So this is actually an important thing to note. And then, as I said, given a mission, we're basically saying condition on some sort of mission, and we're trying to look for its science papers. What are the most relevant snippets? Or in fact, at this stage, we're looking for what are all the possible snippets of text in the paper, which can be something like 10,000, 20,000 tokens, possibly much more. And then extract some of the surrounding sentences, some of the context, because that's useful for determining, is this actually a useful, a snippet that tells you whether or not this is a science paper. We then want to go and kind of prune that down, right? So at this point, we might have something like 100 snippets or 30 snippets of text, right? Which is just a lot of extraneous context. And a lot of these, as I said before, could be false positives. One particularly annoying example is Hubble has an instrument called COS. And if you look for the substring, COS, in any sort of science paper, it will trigger on cosmic, it will trigger on cosine, it will trigger on a lot of different things. And there are kind of ways around that, but you do end up with a lot of stuff that's not relevant. And so using a re-ranker, in this case, we actually spun up our own custom re-ranker because I can tell you the details later, but it's not really important here. You can sort of make a pseudo re-ranker just by using a very, very simple model like GPT-5 Nano or whatever, or 4.1 Nano, and then use that as a way to go and prune out a lot of the not necessary fluff, and then basically impose, I would say, we're only going to keep the top 5 snippets or the top 10 snippets or something like that. At this stage, we can start thinking about what actually should belong in a science paper for that mission. And we actually have another step here where we basically say there's a LLM with a science reasoning prompt, thinking about what is the rationale of, why would you choose, based on these snippets, what is the reasoning for a score you might give, right? Like, do you think that this is a paper that includes science and, say, instrumentation or engineering type observations, and things like that? And that kind of is this free-form text that gets dropped into what I'm calling a reasoning structured output, but it's just a bunch of text. And then there's also quotes that must support that text. So at this stage, the LLM is tasked with this very specific task of saying, like, I want to find quotes that support some reasoning, but finally, it's given very clear instructions in just this last bit of context to say, now given that quote or this collection of quotes or text snippets and these reasons, give a final score. Oftentimes the score will be something like a score between 0 and 1, where 1 is you're entirely sure that this is, say, a science paper or an instrumentation paper or so on. And then, of course, all the other quotes and reasoning and a lot of the prior steps are preserved. OK, so what do these structured outputs look like? So here's an example of a Chandra instrumentation paper that was correctly classified. So you can see that there is some metadata, but what the LLM is really seeing actually is, I realize I have this, is what it's doing is it's trying to make some sort of determination, in this case, a multi-class categorization. So it's making binary classifications of, is this a science paper? Is this an instrumentation paper? Is this just a passing mention? Or is this not really about the telescope at all? Is it totally irrelevant? Because as you know, Chandra also is famous enough that many things are named after him. And so in this case, that's a classification. And it's also giving, it needs to provide this collection of quotes. And so when I say words like structured extraction, what I really mean is that this must be a list of strings. This must be a string. In this case, this is a binary classification. There's also a version of this where we have floating point numbers that must be between 0 and 1. And then you can apply a threshold. In this case, again, we've adapted this for a variety of tasks. So there's slight perturbations to the exact methodology. But the general principle works really well. And the key part here is to make sure that you have quotes that support some sort of reasoning. And then based on these last two things, can we make this final classification? This ends up actually improving our performance dramatically. OK, how do we know it improves dramatically? It turns out that if all you do is chase after the latest large language model variant, I mean, you actually do pretty well. But if you make an evaluation, you'll know exactly how well you do, and you'll know when it's a good time to switch to the next one. In our case, for example, in one of our tasks, we achieved like almost perfect, scores, and so there's probably not a good reason to move on to the next best model because we're already doing good enough. We don't need reasoning chains. All right, so evaluations are really important. Why and how? Specifically, I will talk about a golden sample. There's probably other names for this, golden data set you might have heard. The idea is that you need to have an authoritative source of ground truth. And so this requires multiple passes of human annotation until you reach some sort of a consensus between independent lines of thought. So human annotators who work together and say, oh, I realized that we disagreed on 10% of cases. This is something that's very time intensive. But also at this point, it's important to have a historical sample, not just a golden sample that requires some re-review, but also a historical sample which serves as a calibration of existing error rates. And together, these tell you when you are done with your task. They tell you that if the LLM performance is comparable to the human performance, you've hit essentially your error floor, or your error floor, right? You were happy enough before with human annotation with some possibly assumed to be 0, but actually non-zero error rate. And if your LLM is comparable to that, then you know you're done. OK, just making the point that obtaining ground truth labels can be extremely time intensive. Here's an example paper from 2001, which is titled Molecular Gas and Optically Selected Mergers. There's no mention of Hubble Space Telescope anywhere like in the in the abstract or the title. Unfortunately, even for this case, actually, it's even trickier because the publisher does not allow has made this particular paper unavailable, I think due to some sort of licensing issues. I don't know, I'm sure Kelly or Alberto will tell me exactly what went wrong, but like fine. But if you do look at the PDF for this paper, you'll like notice that there's some Hubble imaging in the background here, and it in fact does mention HST in a caption, and it actually is relevant to doing this particular science. It talks something about like offsets of gas, with optical like high resolution imaging. So it is doing science. It's an HST science paper that is extremely difficult to classify because you have to just find this figure 13 here and be like, oh yeah, this is a HST image, and make that determination. So just trying to make that point home. Let me go and skip through this. Actually, no, I can't skip through this because I promised Jinmi I'd talk about this. So evaluation metrics are, really like, again, the name of the game. So if you have a golden data set, then you know what is the ground truth. If you know which evaluation metrics you're trying to, then you know what you're optimizing against. Again, you're basically defining the meta task at hand. In our case, we're trying to do a couple of, this multi-stage decomposition of papers into some snippets. That's more like an information retrieval task. I'm not going to talk about those evaluation metrics, but there are versions of the typical metrics that are sort of within like the top K or whatever. So you'll see words that like, you'll see metrics that are something like precision at K equals 10 or whatever, recall at K, F1 at K, and so on. But in fact, I'm gonna talk more about this actual classification task. And so this can be, one versus all, like multiple classes, or it could be, categorizing papers as a bunch of binary classes. And so when you're in the case of a binary classification, you can imagine that this is a thing I borrowed from Wikipedia, a little schematic here, showing that you've got a whole bunch of here's all the possible samples. This is kind of abstract now that I look at it, and these are sort of like the ground truths, right? They're the true negatives are out here, and then you've got the false negatives on the outside here. But all the ones that are determined, basically classified as by the LLM or by whatever predictor you're using is being shown in here, right? So you can nicely segment your true positives from your false positives. And ultimately, what the precision is telling you here is the purity of your sample. Thanks. It tells you something like, how, essentially like how few false positives do you have? And you can contrast this against something more like a completeness. Again, if completeness is kind of what astronomers call it, but recall is the term that's being used here. And this tells you something about, the completeness of predictions versus the ground truth or the gold sample. And F1 score is a very useful summary statistic here where you're just taking the harmonic mean between those two. It's a good way to balance the two. And so we use these kinds of evaluation metrics to not only evaluate LLMs, but also human performance, as I said. Okay, some of the results. I know I'm running low on time. We want to be able to identify JWST science papers on arXiv. And just some motivation. It turns out that JWST science papers are required to reference a mass DOI. That's part of one of our requirements. If you're going to do science with some JWST data. But sometimes people will not do that, and they'll also post their papers on arXiv. And that gives us the opportunity to shoot them a quick email and say, hey, did you know that like you should comply with this DOI requirement? Here's like a handy website that shows you how to do that. And so then we direct them to this website down there. And oftentimes people are happy to comply. So this is really good. This establishes provenance and it kind of reinforces this cycle of like we're doing a better job of tracking our literature and knowing that our science is doing well. It turns out that there's a lot of preprints per day, as you know, of which something like 300 or so might mention JWST, but not always because they're doing new science with JWST. Only about 100 or something like that, possibly a little less. Sorry, this is per month, not per day, are true JWST science papers. And so we want to be able to pre-filter out these with extremely high completeness, right? We don't want to miss any of these, or in general, we don't want to miss these, but we do also want humans to go back and review ultimately. And so what we're trying to do is catch these because we need to send them an email. And this automated DOI detection, sort of the next step would be to actually automatically tell if they've got a valid DOI. We do not do this because this is very challenging to do, and so we opted not to automate this part. which means that we now still have humans in the loop. And in fact, this AI system is in operation serving STScI staff. They are now able to skip 2/3 of these papers, right, that might have JWST mentions or something that seems like it's talking about JWST, but is basically irrelevant to their task of finding real science papers. So this is really reducing tedious tasks for real staff, right, who are now using this. And so this saves FTEs and operations. It turns out that we, as I said, care more about completeness. We get something like F1 score on a sample of about 115 papers. That is the NASA flagship mission, so HST and JWST. It turns out we do very well, like as well as humans. We also want to maximize recall, so that really means that we want to make it so that our threshold gives us just more science determinations, even at the cost of potential lower precision or more false positives. In any event, this works quite well. With my last minute, I'm going to say very quickly that ADS also did this really nice Kaggle challenge, and I think Felix, who's he's here at the workshop, did a great job of spinning this up. And what this is, again, is a very familiar task. In fact, so familiar that I was doing this previous task, this JWST preference automation, and then noticed this Kaggle challenge said, wow, like this is almost exactly what we're already doing. So why not adapt the code just a little bit to make it work? There's a huge training set, something like 9,000, 10,000 papers that were used ostensibly for training, but we don't need to do any training, so we can actually just take a peer at a small subset of these as a way to understand evaluations. And the takeaway here is that detailed inspection of data can help you actually understand your own model system better. It can also help surface potential errors in the data or in the training corpus itself. I think this is one of the real valuable things of being able to use LLMs at huge scale, so that you can go and see whether you're making some faulty assumptions, whether in the data or in the model. OK, I'm going to skip past that and just simply say that this is actually written up in a paper, and in fact the code is also public. So we call this AMC, the Automated Mission Classifier. You can go on GitHub and take a look at it. And ultimately, this minimally tweaked version, the system design that I showed before, was able to capture 3rd place on the Kaggle competition. We achieved an F1 score of 0.84. But you should definitely refer to the paper for all the caveats and all the additional details here. I think I'm out of time, so I'm just going to leave my takeaways on the screen here. And thank you for listening.
Thank you so much, John. Do we have any questions?
Yeah, this looks like a lot of interesting applications are possible. For the case of bibliography identification, I think different telescopes have sort of different philosophies on whether we should include new science with data or and exclude the data that is maybe like a comparison, but it's not new science coming with that data. So I'm wondering if your team has considered that. So if they mention, say, a previous result from JWST, and maybe they have a minimal inclusion of that data in the paper, do you include that or exclude it? And it seems like that would be like a hard edge case model.
Yeah, so I think there's a lot of things that could be said about this, and maybe I'll defer to some of the folks who have done that hard work, like Jimmy and others. But what I will say is that LLMs actually allow you to break free from the paradigm of just binary classification of all sorts of things. You can actually just ask open-ended questions, right? You can ask questions like, how, is this a paper that which of these papers are papers that basically were not initially requested as part of the GO program, but ended up being sort of a more valuable archival science case, right? You could also do this in a more traditional way by cross-matching things like authors of the proposals against the authors of the paper and trying to establish which of these are partly archival or purely guest observer or whatever. So I think there's a lot of different ways to answer that question, but I do think that LLMs are really powerful in that they can give you new ways of interrogating your data set or your text.
Yeah, Nick.
Hi, thank you for your talk. Can you expand on the reasoning prompt and why that was able to dramatically improve the classification performance?
Yeah. I think it's better stated that we previously had a failure mode where there would be disagreement between, okay, how do I do this? Between the score that was given and the extracted quotes and reasoning. And this could just be a failure on the capability of the models. This was using like GPT 4.1 at the time, or 4.1 mini. And when I say, again, reasoning here, you shouldn't think like reasoning chain of thought. You should think like there is a specific prompt that says, hey, like, try to give a rationale for why you extracted these quotes. That rationale should feed into, why is this a science paper for that specific thing? And so we realized this two-step approach it added a tiny bit of extra overhead cost and time, wall clock time, like almost negligible, but it did improve the score. It basically reduced all possibility of, the LLM saying, this is like, I think there's a 30% chance this is a science paper, but then the reasoning is like, this is definitely a science paper. And like, aha, here's the magic about how this is a science paper. Like why it was doing that to begin with, I don't know. Maybe there's a skill issue on my part, but we found that this was a good way to ensure that it was actually leveraging its own rationale. Yep.
Okay, we have time for one more. Nolan, go for it.
Yeah, so this system you built works at, finding how influential telescopes are. But you could adapt it to find how influential papers are. Are you just citing a paper just for the related work, or are you citing a paper to build off of it in a whole new way? So like, have you thought about, are there any applications beyond telescope attribution that you're excited about?
Yeah. No, that's a really good point. I think, I'm trying to think if Semantic Scholar is trying to, or maybe has already deployed something like this. It's definitely a good idea, and I imagine that Kartik with Lodestone might be also thinking about similar types of ideas. I think for us, it's this system is meant to be kind of rigid. It really is meant to be a tool that is kind of self-contained, but it does a primary purpose and does it really well. One of the things I'm really unsure about when we expand into research literature is like, how do you evaluate any of that? Everything is so qualitative, right? And of course, like people are extremely biased. People will be like, well, of course, lambda CDM is wrong, right? Like, but all the haters always, say that it's the, default answer. And like people have their favorite theories and things like that. And I think that it's really hard to say, it's a challenging problem that I'm not willing to tackle. Maybe I'll put it that way. Yeah.
Okay, let's thank our speaker again. Okay. John, we need your microphone.
Oh, yeah. That would be a good idea.
Next up is going to be Jinmi.
Okay, can you hear me well? Or, okay, great. Okay, everyone, thank you for giving me an opportunity to talk. My name is Jinmi, and I'm an astronomical scientist data scientist at MASS at Space Telescope. I'm going to talk about this BibCAT project, which is AI-driven automation project for mass bibliography classification. And so before I'm going to talk about the talks, I want a special thanks to my collaborators and contributors. This work wouldn't happen without them. So we have tracked publications related to mass missions over 50 years, and we classify them into sciences and non-science categories, as John said, based on the use of mission data for scientific analysis. The main reason is to help to quantify the productivity and impact of the mission we host at MASS. And this is evident in these two figures published by actually in print by Shah et al. And this is a BibCAT, so I'm going to just quickly give you a quick summary. So this is number of science papers for master mission, and the other one is the citations of these papers. You need to look at this dotted line, HST counts, and then this blue line is all master mission except the HST. Important thing is that they are not only steadily growing, but rapidly growing, and then as you can see in the citations too. So this is really a good example of this by bibliometrics as a measure of the mission impact. And so we have about 8,000 candidate papers from 40 different journals, over 19 missions. We use ADS search to find these papers. And then typical review pace, manual pace, is about 1/3, at least like 1/3 of FTE. It's pretty expensive. And over the 50 years, more than 25 people have reviewed these papers, so inconsistent classification is inevitable. And so with increasing number of these papers, with especially Roman, it's going to be very challenging with the manual review. So we have developed a Python-based automatic classification system using AI to reduce this particular problem, manual workload and cost, and then improve classification consistency and enable more timely updates to publication metrics. So BibCAT is a user-friendly installable software designed for integration into the end-to-end paper track bibliography review system at MAST. And so we actually search papers using keyword searches using mission names and its variants against full text. And then we ask LLM to identify if paper is mission relevant and then classify them into paper types based on the criteria. And then we ask it to output the notes about the paper and the paper types and the quotes and the reasoning to support that decision, and then confidence level per mission per papers. So our design is actually, it's a little bit simpler than what John did. So then we compared the LLM results with our human classifications. And then also we use various OpenAI models and then tried various prompts to improve the metrics. And then we have used like full text versus PDF. They're very similar depending on the papers. You could, one form is better than the other. And then we have also checked the consistency between the single run versus multiple runs. They are pretty consistent within 3 to 4%. So as a pilot study, we use this golden sample, about 200 papers. As John mentioned, this is really extremely expensive and time consuming. So we did multiple reviews by multiple reviewers and reaching to 97 agreement. As you can see here, it's not 100%, even with multiple review. This is showing that how it's difficult to reach to consensus. And this is the performance metrics of this golden sample. This is a lot of numbers here. I'm going to go to going through individual. So I break down the results based on the mission, JWC, HST, and 5 core master missions, and then plus Penn stars here. And then each category, you see the human classification and GPT-5 mini. So here, human means like initial classification of this golden sample against the new golden sample classifications. And then I want you to focus on this F1 scores. So when you compare human versus GPT-5, actually LLM reached the human level performance in each category, which is really exciting for us because it helps us reduce our time. And also, you notice that the F1 scores actually decrease with the more missions included in the category, right? So this depends on many reasons, but depends on the nature of the data products and then how the paper use data products in the papers. So for instance, the JWC is early in the phase, right? Early in the mission phase. So people likely to use paper directly for scientific conclusion. But HST has a long history, right? So the data use cases are quite diverse, and also evolved throughout the 35 years of history. So it gives us really challenging to classify really with a higher performance. And this is evident in the metrics of these 5 core missions. So And another example we plot, I can show you that the reason. So these plots actually showing all the historic human classification from since 2000 to 25, also LLM results. And we use the same basic design for the golden sample and just like run it. And then you see the fuse and test their primary data purposes. This is a spectrum data, and then this is light curve. So most papers use as it is for their own scientific conclusion. So that's why they're very consistent. But as you can see, individual HST and PenSTARs, not mostly, but many of them are actually include imaging data. Imaging data has a lot of application, right? So early on of their mission life, they are very consistent, right? Because in the beginning, you just use the data exactly, right? But then later, over time, that somehow people use a different way. So it starts to diverge. So I'm going to talk about the details about why they diverge. But before going to that, important thing or a very exciting thing for us is that you see the trend of the yellow line is a LLM. That really tracks with the human classification and then increasing. That's really great for us to report at NASA. This is great work. So then what causes this divergence? There's many regions. So both human and LLM have, it's also both different failure modes. First of all, as I mentioned, the data drift. So early on, people used to use it directly for scientific results. But then over time, people use it directly, indirectly, or insignificantly, or supplementary, or sometimes a very subtle way to use the data. So really challenging for sometimes human, actually most of human, but LLM does too. And then also the depending on the model, actually, when we first used 4.0 mini and 4.1 mini actually didn't really capture a lot of these indirect papers. But then with the 5 mini, actually it helps a lot very consistently. And actually we find out the human actually miscount a lot of papers. And then the definition of paper types evolve also. And then there's a lot of room for interpretations. What is exactly science paper, right? That's really subjective. And also because of that, we have inconsistent human classification, right? So this is not just different people, and as a human, depending on your day, depending on how much you have like to do, and your like performance goes differently, right? And then also some of the papers, in particularly actually PenSTARs, actually a lot of PenSTARs have a lot of tabular data only, or imagery, or captions. So some of the texts we have didn't have that information. That's why LLM missed some of them. And also we have a paper track system UI for manual review. And there's some technical limitation because we use a keyword to extract this excerpt, but then sometimes the Kepler or K2, a lot of papers just mention a lot of names. And so we can't really we can show everything, so sometimes we just miss them. And then some mission names are so generic to really capture. So that's a main reason. But so with improvement of prompting, our prompts, I think BibCAT will reduce manual cost and then manual load and then cost and improve this classification consistency. And then we can deliver more timely, insightful publication metrics. And then this is really important point. These advances help demonstrate the leadership, NASA partners, and then the astronomical community and the public, how the taxpayers' money actually really supported the research drives real discovery and it deepens our understanding of the universe. Okay, that's all, and yep.
Thank you so much, Demi. I think we have time for one question.
Can you talk about the process of adding a new mission? Is this pretty straightforward and extendable also perhaps to if you have like a collaboration or something, say if you wanted to measure all the publications from the Candles?
Yeah, it is. So, so the way we did is basically you can add any mission name there. And then we have to, the one thing we have to decide though, what level is the science paper. As long as you have a clear definition, you can just add whatever your missions and then just apply the same thing. Yeah, it's very easy way to do it. Yeah. As long as you have a same data format, yeah.
Okay, great. Let's sync the speaker again.
And Janita.
Oh, yeah.
And Michael, yep, okay.
There, I'll give you 1 minute.
Sounds good.
There's what's on the screen.
Okay, hi. So for those who don't know me, I'm Mike Jones. I'm a staff scientist at IPAC, and I'm working in the Infrared Science Archive. I really just got into LLMs in the sort of last several months, so I don't think we're doing anything revolutionary, but I think we're trying to build a robust tool that will actually be useful and that people can trust. So to begin with, I'm going to give a little motivation. So I'm going to posit that as long as people have been writing documentation, there have been other people who don't want to read it. And this is kind of an ever-growing problem at URSA. As we support more missions and we develop new ways that people can access the data, that in turn means more documentation. And so, we have kind of this sprawling documentation, and that's great to have all these ways to access the data if you're like an experienced user and you're familiar with the tools. But if you're a new user, then this sort of labyrinth of documentation can be a little bit daunting. And so LLMs, provide potentially a good way to resolve this problem by giving people a more convenient way to interact with the documentation and to do some things for you. But we also want the approach, whatever tool we make to be robust. And ideally, it needs to be inexpensive, so it's easy to scale to have hundreds or thousands of users. So an approach that's been talked about a lot, so I'm not going to stress it too much here, is RAG. And this is good because it can be a pretty cheap approach. But just to give you a quick overview again, basically with RAG, you have your documentation, which might be whatever PDFs or web pages, etc., papers. And that documentation gets split into chunks, and those chunks are turned into vectors, and then that's stored in an embedding or a library that is very rapidly can be very rapidly searched. So when I'm going to have a few of these in my talk slide, so whenever you see one of those, that means we're doing RAG. And just to give you an example of how this works, if you have a user query, so when did SpherX launch, that is turned into a vector, and then you search your library for the n nearest neighbor vectors, essentially, to that. And all of those chunks that are associated with those vectors get appended to the user query, and then all of that is sent to the LLM. So you're literally giving it the answer along with the question, and all that it has to do is rephrase and return it to the user. So this is a real example of one of those chunks that has the answer to the question in it. But we would append more than this, but the slide's only so large. So our first use case for this is actually we focused on SpherX. And the reason we did this is because SpherX is a relatively new mission. So it doesn't have loads of out-of-date docs. And it's just a kind of a simpler scenario to silo into its own use case. And we seem to be having pretty good results with this. It seems to give reliable answers. It always returns references to where it got the information from in the docs. So even if the answer is not fully complete, the user can sort of simply jump to that page, and they know exactly where that information came from. So at very least, it's just an efficient way to search the docs, but usually it will also give you the information that you actually want as well. And so we're currently testing this sort of internally, but we plan to deploy a beta version of this in the near future. Another use case is TAP. So if you're not familiar, TAP is Table Access Protocol, which is a VO standard for how to access tabular data. And this uses sort of an SQL-like query string called ADQL. And so if you've never done that before, you've never written an ADQL query, that's a little bit of a barrier. But even if you are familiar with ADQL, it also has hundreds of tables with thousands of unique columns and billions of rows. And so knowing all the right column names and all the right tables to use is another barrier. We currently have some GUIs and things to help with that, but this might be another task that an LLM could just do for you. And so I'm going to show you an example before I show you what's under the hood. So again, this is a real example of how things are running right now. So in this case, the user's just asking for all wise sources that are within certain distance to this galaxy, and then to order them by distance. And so the LLM does a pretty good job of this. It has this distance function that's defined as the distance from M1 to 1, then it's ordering everything. These are real column names, etc., and this is the correct table. So it's done a pretty good job of this. And actually, the hard part of this is not really the ADQL syntax. In this case, we're using GPT-4o Mini. And if you just give it some examples and some documentation about ADQL, it can do a pretty good job. And I think actually the newer models do this out the box. But the tricky thing is actually the table names and the column names, because there's hundreds of tables and thousands of unique columns. So that's actually the part that's tricky to get right. And that sort of directed us to this slightly convoluted approach where we use sort of multiple stages of RAG. So what's happening here is we have the user query, and that's sent in two directions. So the sort of first direction is what you would expect. It goes to some documentation and some examples of queries. But the other direction is the first step is you're just doing a RAG to determine what table do you actually want to access. And then from there, you then go and look at the schema for all of the columns within those tables for the specific tables. And then you put all of that together. And then you generate the ADQL with the final call. And then at the very end, this is not an LLM. This is just a fixed validator to check the syntax. And at the moment, it's not in a loop. So if the syntax is wrong, it just gives a warning to the user that there's a syntax error. And so I have 1 minute left. So just to summarize, so if you have a lot of text-based docs that are sort of sprawling and become a labyrinth, then RAG may be a very useful way for you to interact with that, maybe your own team, but also your users. But it's really important to curate what docs you put into the RAG, because you really get out what you put in. And it's also very easy for RAG to become confused if you have like overlapping documentations, or maybe you have two missions that are doing very similar things and their documents sort of overlap in some of their jargon. And so you might end up getting improved performance if you sort of silo things into niche tasks and maybe have multiple models for different niche areas. We also found that it was very good at identifying out-of-date documentation. So we ask it something that we think is in the docs, but we don't actually get back the right answer. It's usually because it's not in the docs, or the docs are out of date. And we're still sort of building on to improve some of the continuity in this. And as I said, we hope to share the STScI assistant pretty soon, and we're still working out the final bugs in the TAP assistant. But yeah, we hope to expand that soon too. So I'll stop there.
Thank you so much. Do we have any questions? Yeah, Adele.
These are really nice prototypes, so thanks for showing. On the point of the RAG and the documentation curation, have you guys discussed, or are you worried at all that it could actually kind of misinterpret the documentation and send a message to the eventual user that is incorrect?
I mean, so at the moment we have like the model in the background has temperature 0, so it's pretty much copy and pasting the docs. So I don't think it will say anything that's incorrect. It might say something that's irrelevant. Yeah.
Thanks.
Great talk, very interesting. So at the beginning, how much time did you spend kind of fiddling around with embedding models and chunk sizes and things like that to get the maximum usage, proper usage out of the RAG model?
Yeah, so I experimented a lot more with the tap side of things than I did with the spheric side of things. So I think I can't remember the chunk size off the top of my head for spherics, but we didn't experiment much with that. I think it worked fairly well. But with tap, like that's not chunked in a sort of random way. It's you know, the how exactly is it? Like each for example, the example tap queries, that's chunked so they're each an individual query, and so you know with a individual description of that query, so it gets back like the whole query. It's not broken up, and with the tables, you know, there's a separate RAG for every table. So some of the tables have over 1,000 columns, so we have a RAG just for that table. And so that's that diagram that I was showing. Is it actually in this step here, it's actually doing RAG just for that specific table after you've decided what the table is that you want to query, or the LLM has decided what you want to query.
Okay, let's thank the speaker again.
I need to go to the first slide first. Slideshow. Okay. Can you hear me? Yes. Okay. Hello, everyone. I'm Paula Sanchez. What is going on? The slides are changing by themselves.
Okay. View full screen, maybe.
Yes, okay, good. I work at ISO, the User Support Department, and today we'd like to tell you about this tool that we are developing at USD called ISO Finder. So if you ever use an ISO instrument, you may know that we have tons of documents, websites, and it might be tricky sometimes to find where the information is located. So we are exploring within USD how we can use LLMs to improve the services we provide to the community, in particular to help users in the phase 1, 2, 3 processes, and also data reduction and data access. So far, the users have access to this information through manuals and websites, and we also have this knowledge base, which is basically a frequently asked question website. But we think as more instruments are added and the technology evolves, we can do something with LLMs to help the users. So I'm glad that I don't need to define RAG, because this has been discussed a lot during the conference. So what we are doing here is developing a RAG chatbot called ISO Finder that basically uses as a database all the documentation we have available for users. And this work is done in collaboration with Claudio Reinero, one of the software engineers at ISO, and 3 astronomers, Miguel Bioque, Ashley Barnes, and Jod Pritchard, that are helping me to develop this tool. So this is the core of ISO Finder. So I will dedicate some time to this slide. So as we have so many documents, and some of them are quite large, we are using an approach for the RAG that is called contextual slicing, where we have a set of documents that can have several pages. So before we do the chunk of the slicing of the documents, we first summarize the content of the document with an LLM, and then when we do the embedding, we have a version of the summary attached to each chunk of documents. So we cut more or less every document in pieces of 1,000 words, but each one has access to this summary. So then the RAG can understand the contextual information within documents. So then whenever we have a query, we first start with the RAG process, and we do this in 2 ways. So we have a semantic search, like the traditional RAG, but we also have a more traditional keyword-based query with Elasticsearch. And then we combine them, and then we provide this to the LLM. To combine them, we first sort them according to their relevance, and then we give more priority to the semantic search and less priority to the keyword base. And then we will use a re-ranking algorithm to provide the LLM the correct set of documents. And that's the output that then the system sees. But then for the generation of the answer, as we want to be very conservative and only provide information that is available in the documents, we have this loop that allows us to be very constrained to the documentation. So what we do here, whenever we retrieve, we grade again the documents, and for that we have another LLM that is in charge of saying, okay, this document is relevant to answer the question. If we have enough documents, we go to the next step, where we generate, but then we do a hallucination check where we compare not the question, but just the answer and the documents, and we ask the LLM, is the answer contained or not in the documents? If the answer is yes, we go to the next step, which is the answer actually answering the question? And then if that's yes, we provide the answer to the user. If in any of these steps the answer is no, we rewrite the question again, and we go through the whole loop all over again. And we do this 3 times to avoid having infinite loops. So we have this tool now available for internal use at ESO. We have a web interface where the user can ask questions, and then, oops, what do you see? Oh, okay. Oops. I don't know what happened. Where the user can write this question here. You will see in the answer the summary of the documents and also the reference, so you will know always where is the information coming from. But as we are evaluating this tool internally at ESO, we also have a feedback section here where the astronomers at the user support department can grade the quality of the answer using a 5-star system and also a more detailed set of questions for feedback. As this is a long process, like a long loop, the user can also see the status of the process. So you can see how the documents are being analyzed by the loop. And we also now have this tool available in production. So we have ESO Finder included in our DexPro ticketing system. So this is the ticketing system we use to interact with users. So whenever we have a new ticket from a user, the support astronomer will see this agent node with the answer from ESO Finder. As this is dealing with confidential private information, all this system is running locally. We have a server at ESO that has decent GPUs to run this locally and without access to external tools. And then also the super astronomer here can provide feedback about the quality of the answer. So for us, it's very important to understand how good is this tool. So we have this feedback exercise going on since mid-2025. This is the result of the first iteration where we had less documentation, and it was the first version of the tool, basically. So here you can see that according to the experts, so the support astronomers, the answers were on average like 3 stars. And most of the issues were involving missing information. So the answers were correct, but information was missing. So we added new documentation and we did another iteration. And now the feedback is also 3 stars on average, but it's more by mobile. And then the problem here we realized is that sometimes the questions were not possible to be answered by ESO Finder because they were not included in the documentation. So in summary, from this FixThat exercise, we learned that on average, the experts, so the people that know the best the instruments, are grading this with 3 stars. And most of the problems came from the documents, but also problems in the system whenever the system was not able to understand the hierarchy of the documents. For instance, we have the instrument manuals that are like the most important documents for a given instrument, but sometimes the model was using data release documentation, which is very specific for a particular project. So now, in the next steps, we plan to have a system that also understands the hierarchy of the documentation. So this is a summary. So we are using ESO Finder as a tool to help us to navigate this huge amount of documents and websites at ESO. It's a RAG-based chatbot, but in the future we're planning to test other approaches like agents maybe. Currently it's under internal validation, and we hope eventually to release this to the users, but so far it's only for internal ISO people. And we are testing the tool with the real experts, so the people that really know about the instruments. So the next step is, for instance, to try new strategies to improve the hierarchy of the RAG system. And also we would like to create another tool that is dedicated to the telescope operators in Paranal, because sometimes they are working during the night and they need to solve problems quickly. So having a tool that is using as the documentation the operations manuals would be ideal for them. And also we are planning to integrate information from the DexPro tickets themselves. So that's why we're doing this, everything internally, because of course this is sensitive information. And that's it, thank you.
Okay, thank you so much, Paula. Do we have any questions? Yeah.
Awesome work. Yeah, the DeskPro, I just looked up. It's an external tool that I guess you're paying for. And yes. It sounds great. I wonder if you, compared to other tools that are out there, like ServiceNow, for example, and then for the RAG stuff, you were building that. And I wonder if you considered external tools that you could use, like Box and Copilot, that kind of thing.
So far, because we are dealing with sensitive information, we are only using DexPro, and we use DexPro with API calls. So we have an API for ISO Finder. Yeah, we are very conservative in that sense because we are dealing with private information. But yeah, we are happy to explore other options if you think it's a good idea.
Happy to talk more. Thanks.
What I've seen, like there's multiple group of astronomers who are trying to do very similar things, like IPAC, ESO. I know MAST is trying to do the same thing, and I'm involved with the project with Nual Lab, who's also trying to do the same thing. I'm wondering what if people team up to have one mega astronomy portal where...
That would be awesome. I also learning
to the correct servers.
Yeah, I think my take-home message after this conference is that we're all solving the same issues, so we should collaborate definitely.
Okay, let's thank our speaker again. Okay, next up we have Miguel.
Timer there.
So this should I put it here first?
Upside down.
Okay. Sorry. Okay, it sounds okay? Can you hear me? Yeah, okay, perfect.
Okay, put that in a box.
I put this on there. Okay, thanks. Okay, let's get started. Hi everyone, my name is Miguel Doctor and I work as AI solution architect and software engineer for different teams within the data science and archive division at ISAC. Today I want to share with you our experience working with multi-agent systems to support data access and discovery for Euclid mission. So yes, let's start with saying why Euclid is the mission we have been working on focusing for this activity. We just need to see the numbers in the slide to realize how important and how challenging Euclid mission is going to be for the engineers supporting it. We are talking about 20 to 30 petabytes of different data products and more than 200 level 3 science-ready data products that are going to be released by the Euclid consortium and needs to be handled properly. I mean, with these numbers, it's obvious for us that we cannot just rely on traditional methods and techniques to access the data as we have been doing in the last years, because we need something else that allows us to simplify the access and the work for the scientists. In this context, we assess and we work with several technologies, and we conclude that multi-agent systems could be actually a promising technology or a promising approach to handle these challenges that we are talking about. So how do we see the interaction of our scientific community with our archives? Okay, from our point of view, we want our scientists to be able to use natural language to query the archives even when they don't know the data science product format, or they don't know where is the documentation of the mission. They don't know even how to query using AstroQuery, for instance. They don't know how to code this. But we would like to rely on this agentic system to make all these tasks for them. So the science community will just ask for a specific data product, and the multi-agent system will take care of the rest. That means querying the documentation using LLM and RAG, ADQL generation, notebook creation, and these kind of things. So in this context, we created a prototype, and the first approach we follow was to define our own framework, custom framework that allows full flexibility to create our architecture of multi-agents. In this context, we can create different agents that will communicate with different LLMs. We will make use of different tools, and we put them all together to work in order to fulfill the request made by our scientific community. We see how different agents are created, the roles, backstories, the tools, all these things. And then eventually I will move forward, otherwise we will not have time to show everything I wanted to tell you. So once we make the configuration setup, we ask for a specific data product, a galaxy lens in our spectra, and the agents start talking to each other, accessing the documentation, getting the IDs, the format of the products, and eventually they will come up with a Jupyter notebook that has been dynamically created here with the ADQL query and the EQL query that the user needs to execute in order to get the information he was interested on. Okay, so we have validated this idea, and we think it's going to be very promising and facilitate the life of the scientific community. However, it comes with a price. Everything is a trade-off. So in this case, we require from the scientific community to be able actually to code and to use this framework. And we know that it's not always the case. So then we thought, what is the interface that every scientist in the world feel comfortable working with? The web browser, right? So everybody knows how to should know how to navigate, how to interact with the web. So then we said, okay, let's set up a multi-agent system able to autonomously work in the web. Okay, and we came up with this agent Q framework, which is created by these guys here, and there is a paper where they explain that relies on Monte Carlo research for navigating through the web, with self-critic mechanism to select the best possible option, and iterative fine-tuning using direct preference optimization. Okay, this is just more or less the technologies that this framework involves. All the credits are for these guys, but we decided to test it. And in this case, in this demo, I couldn't stop myself, and instead of using Euclid, I wanted to, somehow honor the institution that is hosting this workshop, and we decided to query James Webb Space Telescope archives. So there are two actions here in this demo. The first one is just a basic query about the documentation. So we see how the agents, you see there how they are thinking, they are talking to each other, and they are navigating through the web, getting information about the instruments that are included in the telescope. This is cool, but the really important part comes later when we ask for a specific observation in the European James Webb Space Telescope archive in a position of the sky where we can find the object NGC 3324. This is the interesting part. So then the multi-agent system goes to Google, finds for archive about James Webb Space Telescope information, and it comes to Cosmos Portal. But Cosmos Portal is not the archive. It's a website that gets the agent closer to access the archives. So then it navigates through this website, gets information about it finds this ISAC Science Data Center webpage where links to different archives. It gets information about the James Webb Space Telescope, click on the link, and eventually it will go to the archive of James Webb. It will navigate through the different options, will select the searching, it will type the object we are interested on, and will search for all the observations he asked for. The good thing is that in order to validate that this observation are in the region we are interested on, it also opens a STScI interface to validate this and offer to the user the observation he was interested in. So this is extremely powerful. And the good thing is that it requires no previous skill for the scientific community. And coming back to this issue of removing the need of coding skill from the scientist, I would like to show the third experiment we have been working on, which is AI coding agents. AI coding agents are impacting very hard in other areas of science and technology because it allows to create code cheaper and faster than ever. And in this context, we say, okay, it enables a new paradigm. So you scientists don't want the code. You want the code to achieve a goal, to get information from the archives. So we created an autonomous AI coding agent. We call it ESA Data Science Archives, and we ask for information about it. And the good thing is that it actually gets the capabilities to create their own Python code, their own skills, and it creates a skill for himself to be able to query the archives using curl. But if you ask tomorrow about the same, maybe the agent will decide to use AstroQuery. So it's not relevant for you with technology or with interface you use to get the data. What you care about is the data. And then, as you can see in the prompt, we ask for information, for observation around Carina Nebula. It obtains the CSV file, processes it in a notebook that it's also created here. And once it gets the information he's interested on, he says, okay, the code is no longer needed. I don't need the code because the code, this Jupyter notebook maybe works today, but in 6 months' time, a library is going to be deprecated. So why to keep it? There is no need to keep it. Let's enable a spec-driven development. We care about is the specification of what we want to achieve, the intent. So once we get the information we are looking for, we remove everything and just provide the answer. Okay, so I know this is a bit thought-provoking, but I can assure you this is working very well in other areas. Over in software engineering, there is a new discipline called spec-driven development. And yeah, it's something to keep in mind. So yeah, these are the conclusions. It's more or less what we said, and I hope you find interesting for your use cases. Thanks.
I do like how you just dropped a bomb at like the end of the session, so that was great.
Yeah, just to have something to talk about later in the coffee break.
Yeah, perfect. Do we have, I know we have probably lots of questions. Eric, go ahead.
Yeah, this is all really neat stuff. What scares you? What might the agents do that you're like, oh crap, they're gonna, accidentally DOS us or something? Like, does anything scare you about that?
Yeah, it's very scary, but we need to think that all these capabilities that we are providing the agents with by allowing them execute code or even design their own solutions needs to be properly controlled by using guardrails. Okay, we need to, this framework, the open code agent I show at the end, it has some guardrails where you can decide, okay, you cannot execute this kind of function, otherwise, yeah, who prevents the agent to remove everything in your laptop or to attack the archive. So yeah, it requires an engineering effort from engineering teams to be sure that everything we are enable the agents to do is safe. So this is a big concern, and yeah, definitely something to work with.
Adele, go ahead.
Clarification on the autonomous web agents. You showed this video where you're watching the chat and you're watching the web pages pop up. Are you actually in real time watching web pages pop up on your browser, or was that for a demonstration?
No. It's actually, it works like that. I mean, this is the autonomous web agent platform is built on top of some libraries that allows you to interact with the browser. So the good thing about this second approach that you are talking about, the web autonomous agent, is that it's not just let's say a way to access the data. It's also a way to teach the scientists how to access the data. Okay, so you are kind of co-piloting your request, and the agent will make mistakes sometimes, because sometimes it goes to a web and then it cannot find the information he's looking for, so he has to go back to Google and go to the next page. So yeah, it's promising for people who don't know anything about how to get the information they're interested on. And of course, if you have no idea how to interact with the archives in this web, for instance, or even where is the URL for this is a great solution. But it's more for teaching you how to do it. Because next time you are not going to, to repeat all these steps. Maybe you will go directly to do it by yourself. But yeah.
Okay, we'll squeeze in one last one. Eva.
This is really great. At one point during your talk, it said we don't actually care what the code looks like as long as it gets the same result. And I absolutely agree with it. There's lots of different ways to accomplish the same thing with different pieces of code. Have you actually run tests that you're consistently getting the same results? Because especially if the user is not familiar with the system, they cannot necessarily check if the code is ultimately written is addressing their question.
Yeah, but the thing is, like, I'm not talking about we don't need the source code for anything. Okay, I understand that source code is still the core of the work. We see the full scientific workflow. But when it comes to access the data, when it comes to interact with an archive, I truly believe you actually don't care about the code. I mean, I'm a software engineer, but
get the same answer after repeated queries.
Okay. Yeah, but do you want actually?
No, I don't care if the code is the same. But
okay, no, yeah, but of course, you validate that the answer, yes, there is a word rail and reviewer agent that is actually checking that the information you get is exactly the right one. What we are talking about here is that it's not necessary or it's not needed to actually keep the source code to enable access. This is the idea which was behind this demo, because yesterday in the hacks sessions, we listened people saying, what is tab? What is AstroQuery? People may not be familiar with all these technologies, and at some point, they don't have to. As long as they can get the data they're interested in, why? They are going to, mess up maintenance code, libraries. But of course, this is an approach, this is an idea, and it's open to discussions, and yeah. But I think it will have a place in the future of astronomy data access.
Okay, let's thank Miguel again for this very thought-provoking.
Okay, next up we have poster pops and a few logistical items. So this morning there are 3 posters that are going to be on display. Poster pop folks, please come down. This morning there are 3 posters that are going to be on display in the morning coffee break and 3 in the afternoon coffee break. And we're going to be seeing a sampling of posters from both. So poster pop presenters, please let us know if you're in the morning coffee break or the afternoon coffee break, so we know when to follow up with you. All right, so we'll do that first, and then I'll follow up with a few logistical items.
Shall I start?
Yeah.
Hi. Hello, my name is Aitor. You know us from the very first day when we gave the tutorial, and we are presented here, a little bit the idea that we also present during the tutorial. In this case, I'm focused on this paper, on the poster in the data analysis part. No? How can we create, those agents to allow, users to be able, with natural language, to process, for example, to create a spectra, a light curve, or an image. We are focused on XMN, which is the machine I work with, and SAS, which is the software that we use to process the XMN data. And the idea is to try to minimize the tools that we need to create those tasks. Dockerize and put in a Kubernetes cluster. Do all the magic, so then the query with the natural language can be immediately execute and create the spectral image. It's important to say that it is crucial how to standardize the way we can create those images of spectra. So in that case, the virtual observatory we think is a good place to start with the interfaces, with the standard to be able to homogenize all these queries for the different aspects. And that is something that we use for the visibility checker that we mentioned during the tutorial. We are using one of the protocols that we propose for the bio. And as long as all the missions will stand with this protocol, we can use the agents to query different, services of different missions. And with the data analysis, it's going to be something similar. So that's all from my side. Thank you.
Does it matter which order we go? Okay. Not really, right?
That's hello. Oh, well, I had sent actually a slide with a summary of the poster for a pop-up, but that's fine. All right, I'm Rafael Martinez from AstroAI. And in my poster that will be presented this afternoon, we are exploring multimodality in X-ray astrophysics for exploration of X-ray sources by performing, as you see in the diagram up there, contrastive learning between a representation of X-ray astrophysical sources directly from events. We don't deal with images, we don't deal with spectra, we deal with individual photon recordings. We embed those data objects with a transformer-based encoder. And then we also use summaries about the astrophysical sources that have been extracted from the literature, working together with the ADS, and create embeddings with an LLM, OpenAI's GPT-4o Mini. And then we take the two representations and do contrastive learning between the two representations. We are investigating whether that combination of the two embeddings augments the information that we can retrieve from the data by testing this system in the downstream task of regressing on relevant astrophysical properties for the source. And what we do find is that, in fact, when you combine the representation from the text describing an astrophysical source and the data itself, you perform, for the majority of regression tasks, better when you take the aligned representation that we have aligned with contrastive learning, regressing on a number of quantities, both quantities that are observational, like hardness ratios, and more model-based, like a power law or spectral fits. So if you're interested in learning about how we can use that for anomaly detection, for cross-model retrieval, or even for building a system like Ryan will present later to investigate X-ray sources, come talk to us. Thank you very much.
How's it going, y'all? My name is Ryan Thill. Collaborated with Rafa and the team over at AstroAI. I am the founder of a company called Liam, actually formerly called Astromind. We changed our name, but anyways, the app that we built, we call it the Astromind X-ray app. Essentially what it is a multi-agent system that takes in raw Chandra event files. The first thing we do is we create a compact representation of that information using our X-ray processor. So that's a transformer that we use to create that representation, and then we use question and answer pairs that we derive from literature to fine-tune a 7 billion parameter Quinn model so that we can take in the raw event files and get an answer with that first agent. The second agent we have is a metadata analyst, where we calculate roughly 40 spectral and variability metrics that we can do algorithmically. We have a nearest neighbor analyst that we found to be really helpful as an agent, where across about 50,000 sources, we're pulling the 10 nearest neighbors to the source that we're looking at for additional context. We have a tool agent that can pull multi-wavelength data if we need it for things like source type, if you don't have enough information in the X-ray observation. And then we have a critic and moderator that kind of consolidates all that information and provides a final answer to the user. So the kind of end goal and output is that you can take raw Chandra event files and get fast, reliable interpretation and analysis of that source.
Hello, I'm Lorenz, and I'll be standing by my poster today this morning. It's called XMM GPT, and the project itself is a sort of general agent for XMM Newton-related tasks. If you were there for the tutorial on Monday, you've heard me talk about it a little bit, but essentially it's supposed to be an agent that can perform basic tasks such as just Q&A over documentation or grabbing target visibility, to a little more complex, like generating fully fledged SaaS products from just simple user prompts. And if you want to know a little bit more about the in-depth and the technical knowledge of how this works, then come and ask me about my poster. Thanks.
Okay, 5 logistical items, and then we will wrap up this morning's session. So the first, when we come back into this room, we've got another set of talks, and then immediately following that is going to be a group photo out on the front stairs. So emotionally prepare yourselves for having your photo taken. That's coming in a couple of hours here. The second, after our afternoon coffee break, we're going to reconvene in here, and I'll give some sort of low-lift guidelines for what our hack group presentations are like. So right now you don't have any guidelines for that. Those will be coming this afternoon. So that's when you'll get that. Next, at the end of the day today, you'll see an event on your calendar that says STS. That is beer and snacks in the cafeteria. So please stick around, come enjoy beverages, come enjoy some food at the end of the day today. Eric, can I borrow your question as a conversation starter and suggest that we all ask one another, what scares you during today's coffee break? All right, and last logistical item, let's head to a coffee break. Please be back here at 11:15.